Hello everyone, I'm Jaren Mane and I'll tell you a little bit about our latest ICML paper on the hardness of probabilistic neurosymbolic learning. This is joint work with Vincent Kinderen and Luc de Raat. So what is this paper about? Well, consider a probability distribution over Boolean random variables. The problem we study in the paper is how to get the gradient of the marginal of this distribution. We make two contributions in this paper. One is about the hardness of this problem. So when can you tractably not only compute but approximate this quantity? And the second one is a new gradient estimator called WeightMe, which achieves state-of-the-art results. Okay, but why would you care about this? Well, the answer is in the title of this paper, namely Probabilistic Neurosymbolic Learning. In probabilistic neurosymbolic learning, we typically take a probabilistic model, say for instance a Bayesian network, and reparameterize it with neural networks. So in this example, in the image below, you can see an image of a sky, which is interpreted by a neural network to predict whether it rains or not. And then this probability is used in the Bayesian network instead of some hard-coded probability. Now, when you want to do learning in this setting, you need to do both probabilistic inference, which usually amounts to taking marginals in your Bayesian networks here, for instance, and you need to learn with your neural network, so you need to take gradients of this probabilistic inference. And that's how you get to this quantity we started with, namely the gradient of some summation. Now, it's well known that marginalization is a hard problem. So when you take the full joint probability table, you have 2 to the x number of terms, where x is your number of variables here. Now, for taking the gradients, this is the same. Due to the linearity of the gradient, you can see this gradient as just summing over all the gradients of your individual probabilities instead of summing over all your probabilities as you would do in regular marginalization. Of course, this is a well-known problem, and people have studied this for a long time about how you can make this tractable by using some structure in your distribution. So what kind of distributions do we look at? Well, we look at weighted propositional formulas. So in this case, you can write your probability as independent Bernoullis, so some product over all your individual probabilities, times an indicator function. So this indicator function is a propositional formula which kind of filters out which assignments are possible and not. So for example, you can take a formula here, which represents whether your grass is wet. In this case, you say, well, it's wet when it's raining or the sprinkler is on. Then you add some more information, namely, if it's raining, I'm not going to put my sprinkler on, sorry. And I do know that it's wet. Well, then you can calculate this probability by summing over all these possible words, as you call them in logic. So in this case, you multiply the prior probability of being wet times rain times the sprinkler is not on to get the first probability of the first model, and so on. Now, why is this a relevant thing to do? Well, this is kind of a very low level, a kind of assembly language for probabilistic reasoning, and a lot of existing tractable probabilistic models closely relate to this formalisms. For example, Bayesian networks or other models such as factor graphs or probabilistic logic programming can often easily be translated into weighted formulas. And also inference on these weighted formulas is a well-studied problem, and doing a marginalization on it is also better known as the weighted model counting problem. Now, so first thing we do in the paper is look at some complexity results. So first observation you can make that because the weighted model count is linear, we can decompose the gradient, in this case the partial derivative to be precise, as the difference of two conditionals. So this is a simple observation, but it has some consequences, namely one, that you can that calculating this partial derivative is sharply hard because it's just reducible to the original probabilistic inference problem, which is known to be sharply hard. And the same can be done for approximations. So epsilon delta approximating the partial derivative is still NP-hard. What do I mean by epsilon delta approximations? Well, an epsilon delta approximation is kind of a probabilistic bound on the relative error. So you say that the relative error is going to be small, so lower than some epsilon, in most of the cases. So these results show that just like probabilistic inference, taking this gradient is going to be a hard problem. Now we can also look at the bright side and try to find some problems where calculating this gradient, or at least approximating, becomes tractable. And in the paper, we do prove that you can tractably approximate the gradient at some point as the neural network optimizes. So what's one intuitive way to look at this? Well, when you start training, and so you have not done any pre-training, usually the neural network is quite uninformed, and all the possible worlds, so all these possible assignments you can make to your individual binary random variables are quite uniform. So the neural network at initialization typically doesn't have any strong preferences. And so finding one of these models is typically going to be become very hard because they are typically very sparse. However, as the model trains, it becomes more informed and it will start to put more confidence into one of the correct models. And this means that sampling it becomes easier, and that at some point you can get a guarantee that the gradient will be approximate in polynomial time. Okay, but so what do we do if we want to get gradients in the general case, so even at initialization? Well, one thing you can do is rely on set solvers. So even if a problem is NP-hard, these days it might still be reasonably feasible to do, because set solvers, which solve an NP-hard problem, have become quite good in the recent decades. And so in the paper, we prove that getting an epsilon delta approximation for the gradient is possible under some mild assumptions when you do a logarithmic number of calls to some set oracle. And so WaitMe implements this more practically. So how does this work? Well, there is some weighted mole distribution. So this is the probability distribution of all your possible worlds. And then you sample directly from this distribution. Now, doing this sampling is the hard step. So this is an NP-hard thing to do. But there have been previous works that show you can do this, or at least approximately, in a quite scalable way. And then when you have this, you can approximate the logarithm of the weighted mole count using these mole samples. So this gives you an unbiased estimator and also gives you this guarantee of epsilon delta approximation using a constant number of mole samples under some mild assumption. We also have some experiments. So in this experiment, we look at the difference between a variety of approximation methods compared to the true gradient. Then we show that compared to all existing gradient estimators, WaitMe achieves has much higher fidelity, so it's much closer to the true gradient. We also show that WaitMe is typically faster than other methods which are NP-hard, and so do some solving. And on the other hand, that's when you do have some methods which are designed to be polynomial and so approximate in polynomial time and will generally outscale WaitMe, that these methods typically really struggle to optimize. So that's kind of shows that there is a point to be made to use NP-hard gradient estimators. All right, thanks for watching. If you want to know more, I'll recommend you to take a look at the paper.